So in our last example, we did the area that was inside one curve, now that's defined with a polar function. Now we are going to find the area that is bounded by two curves. Now this one specifically says area inside this one and outside that one. That is something that you'll need to pay attention to, because sometimes it might be like maybe inside both, or maybe inside one, outside the other, that kind of thing. So let's go ahead and get a look at what those graphs are first. Probably better if I had polar paper on here, but I don't. So we'll just get as close as we can. All right, that looks pretty good. 6 cosine theta. All right, a couple ways to think about this one. If you know what this graph looks like, it's not too bad. But I could also say that this is a rose with a petal length of 6 and 1 petal. And 1 petal might be like, how is that a flower? Okay, well, let's think about what happens here. If this is cosine, so I'm starting out at the tip of the petal, which would be 6, all right? And I'm curving towards the origin, but I only have 1 petal, so I'm going to curve right back out to the same spot. So I get this. Let's pretend that landed. Sure, we'll use this circle, but can I move it? Maybe? Oh my goodness, look how good that is. Okay. Totally drawn by hand. All right. So this is R1, and then for R2, we have a cardioid. It is a cosine cardioid with a positive middle term, so it's going to be one of these shapes. And our biggest radius is 4, so we'll call that 4. And our smallest radius obviously is 0. And then when theta is equal to pi over 2, so when this is 0, we are 2 units out. So let's say somewhere about there. Okay, and remember this has a height of 3, because this one is just, oh, I didn't talk about why it's a circle. It's just, yeah, 6 times cosine theta, or a number times sine or cosine theta, is a rose with 1 petal, but it just turns out to be a circle. Okay, if we only have 1 petal, it's a circle. You can graph some other ones and try it on your calculator if you'd like, or by hand, but that's what it ends up being. Okay, so then we're going up to 2 and down to -2. So something, I know I'm drawing it backwards, but it's easier for me to go that direction. Okay, so here is our figure. We talked about in the 9.8, at the end of 9.8 notes, about how we need to find the intersections, but we also know that the intersection might not give us, like algebraically finding the intersection might not give us all 3 intersection points. So we do need to pay attention to that. So I'm looking for 1 here, and then I know that this is when r is equal to 0, and then 1 right here. Okay, so then let's find that. 6 cosine theta is equal to 2 plus 2 cosine theta. All right, so let's subtract. So we have 4 cosine theta equals 2 cosine theta equals 1/2, and we know that that happens when theta is equal to pi over 3, which seems reasonable for this. Oh, that's not a, thought I was going to make a line. Nope. Oh, now it doesn't want to make lines for me. Okay, whatever. For pi over 3, and then also in quadrant, cosine is positive down in quadrant 4, which is going to be 5 pi over 3. Okay. Which is this one? Why is it not turning into a line? Hold on. Nope, doesn't want to make itself straight. Okay, whatever. So I'm looking for the area that is inside R1, but outside R2. That is this region right here. My highlighter is a little bit too, there, a little bit too big, but I'm looking for this region right here. Okay, so as far as figuring out how to express that, we could actually do it a couple of different ways. Think of it in terms of sectors though, okay? I do see that I have symmetry, so maybe I just do the top half of this and then I double it. Okay, so that's one thing that's a pretty common option. Also, even though I called this 5 pi over 3, I don't want to include anything over here. So I could also consider this to be negative pi over 3, like to get down here. So I could also go from negative pi over 3 to positive pi over 3 to get this region. Okay, I'm going to go with the symmetry option though. So what I'm looking at is I'm looking at sectors that are inside R1, which would be everything. I'm only drawing some of them, but up to from 0 to pi over 3. But then I am going to take out all, let's use a different color. I'm going to take out all of the sectors that are inside R2, which is all of these. So it is still subtracting bigger minus smaller, but it is not top minus bottom. It is outer, bigger radius, minus inner, the smaller radius. Okay? So how do we express this? Okay, I'm going to do area, and like I said, I'm going to just do part of it and then double it. So I'm going to do 2 times 1/2, and you can do this as 2 separate integrals or 1 altogether, but it's going to be the integral from 0 to pi over 3. And then here's the other thing I need to be careful of. It is not R1 minus R2. It is R1 squared because I'm doing the whole sector minus R2 squared, the inside sector. So R1, which was 6 cosine theta squared, minus R2, which is the whole quantity, 2 plus, I know I'm off the graph or off the screen here, 2 plus 2 cosine squared theta d theta. All right. We could do this separately. We could do, just the big part, the part inside the circle, and then subtract the part inside the green limosome, but this combining it will work as well, as long as you are squaring these individually instead of trying to do them separately. Okay, and then classic. All right, last one. Oh, hey, look. All right, we are looking for the area that is inside 3 plus 2 sine theta. Let's call this R1. R1, which is a Cardi A, so that's the outer one. It's sine. It's going to look like this. That's Toad's hat. Okay, so this is R1. And then outside the circle, R equals 2. This one doesn't have a sine or cosine because it's not oriented differently. It's just centered around the pole, centered around the orange. So this is R2. All right, graph is already given to us. We are looking for area. I would really recommend that you pause the video and give it a try. Hopefully you have done that. What I'm going to do is I'm going to look at this in terms of symmetry. So I'm thinking about this intersection. So from this theta value, and it's okay to give this a negative theta value, up to pi over 2. So I'm going to do this whole thing, and I'm going to do the outside curve and then subtract the inside curve from that. Now, there will be times where you might need to do a different region for a different interval for different parts of the curve. Okay. In this case, though, the big R squared minus the little R squared will get us the region that we want. Okay. So let's write, and I'll show you an example of the other one here in a second, but let's do an example of this. So first of all, we need to know what our intersection points are. So 3 plus 2 sine theta is equal to 2 when, okay, so that's it's all right. So 2 sine theta equals -1 when sine of theta equals -1/2, which is when theta equals pi over 6. Nope, negative pi over 6 because we want it to be negative, which happens in quadrants 1 and 3. So, I know we're gonna use negative pi over 6, so I'll just leave that. That would also be 11 pi over 6, or over here in quadrant 3 for this other intersection point, which I don't really need to know because I have enough information, but it's going to be 7 pi over 6 if we were going in the normal counterclockwise direction. Okay, this is the one we're going to care about though, and we also know because of symmetry that we can stop at pi over 2 and then double it. So I'm going to do the area equals 2 times 1/2 of the integral from negative pi over 6 to pi over 2 of outside function squared, so 3 plus 2 sine theta quantity squared minus inside function squared, which is just the circle, 2 squared. Also, anytime you have a circle like this that's just radius equals a number and you're doing part of that, you can do that geometrically. Like you could do just one integral and then just say, well, this is just a third of a circle that has a radius of 2. You'll get the same thing. Okay, and then that would get us to our answer. Let me give you an example of a graph real quick, just so that you can see what I'm talking about where you might need to use more than one interval. So this second one is, this last one's poorly drawn, but let's say that I'm trying to find the area that is in between these two. So I would start, well, I would need to know this intersection. I'm just going to call that alpha. I would be integrating on the circle from 0 to alpha. So I would do 1/2 times the integral from 0 to alpha of the circle. We'll call that R1 squared d theta. But then I would add, now I'm integrating with the limacone, so 1/2 times the integral from alpha, oh, I guess I could stop at pi over 2, can't I? Yeah. To pi over 2 of R2 squared d theta, and that's going to get me my total area.